Our last video in the equilibrium chapter is going to talk about the solubility product constant. And that's where we briefly talked about this with our KEQ of our heterogeneous substances, where if you have a solid that is going to be in equilibrium with its two ions that make it up, you don't count the solubility of the solid in the KEQ equation. Okay, so the KEQ equation is now called the KSP equation for specifically solubility. All right, so this is just a more specific type of KEQ equation. All right, so if we take silver chloride, AgCl, we know that we have at equilibrium a saturated solution where we should have a certain amount of our two products. Okay, so if we have AgCl, we have Ag plus aqueous and Cl minus aqueous. And I can't stress enough the importance of ions. I've said it ever since November. Ions, 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 always and forever. Okay, so we don't count the heterogeneous solid in here. So the KEQ, or now because we're talking about solubility specifically, is going to be the product of the two ions in the solution. If you have something like CaF2, which is a solid, remember, calcium's a 2 plus, F is a 1 minus, so you are going to have two fluoride ions in there. So the KEQ or KSP value expression is going to be Ca2 plus times the concentration of F minus squared. Okay, so if you remember back to our solubility stuff, this guy has a dissociation factor of 2. This equation has a dissociation factor of 3 because every one of these is going to make one of those and two of the F minuses. Okay, every one of these makes one of the Ag pluses and the Cl minuses. So that's why they have different dissociation factors. Ions, ions, ions. I promised you we would use them all the time. So in our modern chemistry book, table 3 on page 615 has a variety of KSP expressions. They are different for every substance. They're different for every temperature because we know that solubility is greatly affected by the temperature. So here we are going to talk about at room temperature at 25 degrees Celsius or 273 Kelvin. Okay, the KSP represents the product. That's why it's K solubility product of the molar concentration of the ions. This is not what we went over in the solubility curves, okay? This is not how many grams. This is just going to be the product of the two, and that'll tell you what the equilibrium rate will be, all right? And that's pretty important. So you'll notice that there are no units for these. All right, that's because it totally depends on what the dissociation factor is. Is your dissociation factor 2? Is it 3? Is it 4? Depending on what kind of ions you have going on here. So you'll recognize some of our favorites. Ooh, and some that we haven't gone over. That's iodate. But you'll see that they are specific to each one of your substances. All right, so go get your calculators. This is really important that you practice putting these in the calculators because we're going to be working forwards, backwards, and with a little bit of fun extra algebra in there. All right, so first it says calculate the solubility product constant, which is the KSP for copper 1 chloride, given that the solubility of the compound is 1.08 times 10 to the negative 2 grams per 100 grams of water. All right, so always start off with a KSP expression. Okay, the KSP expression is going to be from the reaction. So do the reaction. Cu 1 plus Cl minus make, oof, that's a horrible one, CuCl solid making Cu plus and Cl minus aqueous. So what's my KSP expression going to be? It's going to be the concentration of Cu plus times the concentration of Cl minus. Well, first things first, we have to figure out what the KSP is. We need to figure out what the molarity is. That's right. Molarity is moles per liter. We have grams per grams. So 1.08 times 10 to the negative second grams. We are going, this is, sorry, right here. This is CuCl2. So I look on my trusty best friend periodic table. Copper chloride is going to be, copper is our 63.55 grams. Chlorine is 35.45. Molar mass is 99 grams per mole. So I get 1 mole CuCl2 here, 99 grams here, and then I'm going to take the 100 grams of water and change them into my moles, or sorry, milliliters. So 1 gram of water is 1 milliliter of water. And I know I have 1,000 milliliters of water in 1 liter of water. So through the beauty of dimensional analysis, I get moles per liter. So my molarity is going to be 1.09 times 10 to the negative third molar. Okay, so what's my KSP value going to be? Okay, KSP is equal to the concentration of 1.09 times 10 to the negative third molar times the concentration of 1.09 times 10 to the negative third molar. Don't forget how to put it in the calculator. Okay, so in my calculator, I would put 1.09 e negative 3 times 1.09 e negative 3, and I get a value of 1.19 times 10 to the negative 6. That is my KSP value. Okay, so here you'll see I need my concentration in moles per liter, so grams per grams turns into 1.09 times 10 to the negative third molar. I plug in my 1.09 times 10 to the negative third and 1.09 times 10 to the negative third, and I get my 1.19 times 10 to the negative 6. Okay, so you can compare it to the concentrations in your KSP container, not container, in your tables to make sure you did it right. So now let's go backwards. All right. So calculate the solubility, which is the same thing as molarity, of silver bromide in moles per liter, molarity, if the KSP value is 5.0 times 10 to the negative third at room temperature. All right, silver bromide, that's AgBr, making Ag plus aqueous plus Br minus aqueous. So what's my KSP expression for this? My KSP expression is going to be the concentration of Ag plus times the concentration of Br minus. Well, if my KSP value is 5.0 times 10 to the negative 13th, what are these guys going to be? Well, my dissociation factor is 2, correct? So if my dissociation factor is 2, all right, my concentration of Ag plus is going to be equal to the concentration of Br minus because they break up into 2 equal things. This one thing breaks up into 2 of those things. So if this is equal to X, so is this. So plug in X and plug in X. What does that mean? 5.0 times 10 to the negative 13th is the same as X times X, or X squared. How do I get X by itself? You got it. Square root both sides. X is equal to the square root of 5.0 times 10 to the negative 13th. In your calculator, don't forget to use the square root button, and then 5.0 e negative 13, and you get your value to be 7.1 times 10 to negative 7th molar. So then this is your concentration. Come on. Why isn't that working? The concentration of your Ag plus is 7.1 times 10 to negative 7th molar. And the concentration of your Br minus is also 7.1 times 10 to negative 7th molar. So now I think your wheels are turning. What if you don't have the same amount? This is easy. The dissociation factor is 2. So you do the square root of 2. Let's try the penultimate problem of the year, where everything comes together. Calculate the solubility of lithium carbonate in moles per liter, that's your molarity, with the KSP value of 1.7 times 10 to the negative second at 25 degrees Celsius. Tell me what lithium is and what carbonate is. Lithium carbonate is Li2CO3. That's my solid. Okay, so I make Li plus aqueous and I make CO3 2 minus aqueous. Do I make the same amount of each? No, I have 2 lithium ions. My dissociation factor over here is 3. Every one of these makes up 2 of these and 1 of those. So what is my KSP expression going to be? KSP is going to be concentration of Li plus squared times the concentration of CO3 2 minus. All right, so what am I going to plug in for my values? All right, I know that my solubility expression is 1.70 times 10 to the negative second. What am I going to plug in here? Well, if I have a dissociation factor of 3, it means I have twice as much Li as I do CO3. So my concentration of CO3 2 minus can exist as X. My concentration of lithium will be double the amount, 2X. So I'm going to put 2X here, and I'm going to square it, and I'm going to have the concentration of CO3 2 minus my carbonate as X. So what happens when I do my algebra? 1.70 times 10 to the negative second is equal to 2x squared, which is 4x squared times x. So that's 4x cubed. How do I get x by itself? First, I have to divide by 4 on both sides. So that means I am going to get x cubed equal to, so I put 1.7 times 10 to the negative second divided by 4, and I get 4.25 times 10 to the 1 to negative third. And then I take the cubed root, which is that special button where you'll see an X like this. You have to put a 3 in front of it. 4.25 times 10 to the negative third. And I get X equal to 1.62 times 10 to the negative first molar. All right, that's what happens when I take the cube root of both of those. So what does that mean for my concentrations? That is my concentration of my carbonate, 1.62 times 10 to the negative first molar. What does that mean for my concentration of lithium? Well, it's got to be double that. 2 times 1.62 times 10 to the negative first molar, which is going to be a concentration of lithium equal to 3.24 times 10 to the negative first molar. All right, so you can see that worked out in our notes. You're going to say that you have to be very careful with these. All right, lithium has 2 ions that are produced for every one of the CO3. The dissociation factor is 3. There's more lithium than there is carbonate. Their concentrations are not equal. You can't have them both equal to X. So if you choose CO3 2 minus as X, then the concentration of lithium